So these rocks are going to blow your mind, Victor. But before we get there, we got a lot of time for snacking on the route.
Put food on my plate, that's a coke in my cup. Give me some chicken, bakes and fries, living past me and lettuce on my passage by. So keep shoveling onto my plate. Give me some sweets and a lot of cake. Give me some hot macaroni and cheese. Give me some more food, please. Give me some bologna, salami and ham. Toast with butter and strawberry jam. I love it whether the food is cold or hot. Put a burger on the plate and it'll hit the spot. We'll eat everything in an incredible feat. $3.99 for all you can eat. All you can eat.
Alright, we're all fueled up, ready to go. Let's hit the rock. We're off on the hunt for manganese oxides. We met sedimentologist Dave Loop along the side of the road. He's one of the specialists when it comes to the strange formations we were on the lookout for. Location was an old dugout in the hill with a strange sifting box just down the slope that the miners must have used to high-grade the ore. The way in wasn't arduous, but was difficult to find, off the road and off the trail. This shiny black, purple, and red sheen was what they were after and what we were after too. We're here in Flatiron Mesa, close to Muleshoe Wash, just south of the La Salle Mountains in southern Utah, on a cold November day, looking at some beautiful examples of mineralization of iron oxides and manganese oxides that were precipitated along faults here and in other regions near the faults in sandstones, the Navajo sandstone. And the reason we're interested in these deposits is, one of the reasons we're interested in these deposits is because we understand a lot about groundwater today. We understand a lot about modern groundwater, how it flows through the rocks inside the earth, how to get it out, how clean it is, the water quality, how much we can pump out, but we understand really very little, relatively, about paleo groundwater, about the geologic record of water moving through the shallow parts of the Earth's crust. And one of the best ways to try to figure out what we can learn from these types of minerals that are left behind from paleo groundwater is to go to places where a lot of focused flow of groundwater has occurred in areas like this, around faults. Look at the minerals that are left behind and see what we can say about the ages of these minerals, and therefore the ages of the groundwater flow, and also the chemistry of these minerals, and say something about what the groundwater composition was like, where it was coming from, and what its evolution was. So here we have, in this area near Flatiron Mesa, or in Flatiron Mesa, we have minerals that are minerals of two different types that are precipitated. Most of the stuff around here, almost all this black color you see here in these this old diggings that was excavated out probably in the 40s, is manganese oxide, and that's what this dull colored precipitate is that kind of rubs off on your finger. But there's another type of precipitate here from the groundwater, and that's this slightly shinier, more coarsely crystalline material. This is iron oxide, and so in some places we find iron oxide and manganese oxide precipitated together in the same vein, or in the same kinds of bushy structure that permeated out into the sandstone. In other places we find them very much separated. We'll only find the manganese, or we'll only find the iron. And whether we find them together or separate, and the patterns in which we find them, tell us a lot about the composition of the groundwater, how oxidized it was, and how it evolved through time. So we could say something from the patterns about how this groundwater system evolved through time, and then by radioisotopic dating of these different deposits, we can say when the system was active. And the preliminary dates that we have from this area already suggest that there was a lot of water flowing through these faults and coming up to the surface somewhere between about 2 and 3 million years ago. And this is interesting for a number of reasons, one of which is that this is a time when the climate that the surface of the Earth was changing very dramatically, and we were entering a series of ice ages 2 to 3 million years ago, and the whole hydrologic regime of this area and many other areas was changing. These oxides were covering the length of the fracture, and we needed a sample. Some geologists use rock hammers. Those are the weak ones. All right. So in this part of this outcrop, you can see a couple of different kinds of mineralization from this paleo groundwater. One is the manganese oxide cement that is filling in the spaces between the sandstone grains here, and that's what makes a lot of this area interesting and poses a lot of interesting questions for us. But sometimes when we're trying to figure out the actual age of this mineralization and age of the groundwater flow, it's better to go to this material, which is the pure manganese oxide that forms right in the fracture, in the fault itself. It contains no detrital sand grains, and it's much easier to date, has high uranium concentrations, and produces very good results for our radioisotopic dating. Just over the hill from this fracture was an even more spectacular location of intense outpouring of manganese from the groundwater. Up close, these looked a little like giant broccoli florets. Richter had already discovered these and was labeling and collecting from every joint and fault like it was a crime scene. The goal was to collect samples and analyze all stages of hydrothermal alteration, from the fresh, unaltered material to the intensely mineralized rock.
Well, here's the plane of the fault. There's several faults in here, but you can see where the movement of the rocks on either side scratched the rocks, slickened sides. And then the reason we're here, though, is to look at what the waters that have moved along the fault and into the rock have left behind. And so this gray rock has its origin from the waters bearing the metals moving out, and there's one big mass that made of those cauliflowers, and here's another one down here, and you can see the growth stages of as the minerals built out into this sandstone. So clearly this is a zone where waters that were transporting manganese and iron in solution met oxygenated water. And so this interface between the water that could carry the iron and the water that could cause it to come out of solution, they were sort of battling across this front. And I'm intrigued by the possibility that microbes may have played a role in this. In here you have what could be called little shrubs or dendrites that branch to make the overall cauliflower structure, and sometimes microbes can generate those. And we haven't imaged these yet with a scanning electron microscope, but it seems like there's potential for that. And I say that because with manganese oxides, if there was no life involved, it would take a large concentration of manganese in the water at any one time to cause it to precipitate out. But if microbes are involved, manganese oxidizing microbes, they can take really dilute water that's carrying manganese in solution and take the manganese out and get energy from it. So that's one possibility here, that there's a lot of manganese because of the action of microbes that lived at this boundary between the oxygenated water and the metal-bearing water that was coming out from the fracture.
So these minerals provide very good evidence for the paleo groundwater flow that was happening here 2 to 3 million years ago, but in a very restricted region where the faults were channeling up groundwater. In another area we're going to go to, you're going to see some very spectacular examples of precipitation of minerals over a very large region in a pervasive aquifer groundwater flow region. And these things are called Moki marbles pipestones, and a lot of other interesting names for these bizarre features that we don't quite yet know how to interpret. Now we're off on the hunt for the Moki marble.
Here's an in situ marble, and you can see it's not your typical concretion, which would be solid throughout. You know, the pore filling cement would be throughout, but here the iron oxide is restricted to this rind, and our interpretation is that this was a typical concretion, but composed of siderite and iron carbonate. And carbonate minerals are famous for making spherical concretions. So FeCO3 throughout, and then that's under reducing conditions. Siderite's only stable under reducing in reducing waters. And then as the Colorado Plateau is uplifted and the canyons are cut, oxidizing water starts to infiltrate this porous sandstone, and microbes, iron oxidizing microbes, can get their energy and their carbon from the siderite. So it's a perfect growth medium for iron oxidizing bacteria. And they set themselves up at this redox boundary. In other words, there's oxygen outside and ferrous iron inside in solution, and their metabolism generates the iron oxide as a waste, and they derive all their energy from transferring the electron, go from ferrous to ferric iron.
From the beginning of our hike in Escalante National Monument, we could see evidence of how these little critters formed in the sandstone millions of years ago. As we hiked further in, these little guys became more abundant, filling all the valleys around the sandstone. Every low-lying dip was covered in marbles. You might wonder how this happens. Here's a Moki still stuck in the rock that needs about another 1,000 years to be liberated.
These concretions are typically spherical, and they weather out in relief because they're composed of iron oxide, tightly cementing the sand grains together. So around here, there's the sand grains, they're lightly cemented, and so you can see this one's weathering out in relief. When these things finally weather out, get released from the sandstone, they roll down the slope and join hundreds, thousands of others in just big piles. And you can see a lot of them were singles, but a lot of them grew together and formed these masses. And looking at it here, it looks like they're solid, but you break these open and you can see there's a rind of tightly cemented sand, cemented by iron oxide, and the interior was soft and it's fallen out with these. There's another one. And so a typical concretion would have cemented material throughout the sphere, but these aren't typical concretions. They started out as an iron carbonate cement, but then when oxygen came in, bacteria, microbes, colonized the perimeter, and they were able to maintain a position between where oxygen was and where dissolved iron was. And so they occupied this redox zone, and they were able to get carbon and energy out of changing the ferrous iron into ferric iron. So this is ferric iron in the form of iron oxide. So these are concretions, but they're not typical concretions. They had a precursor. So in the first phase, you had the concretion growth in an area where there was no oxygen, and then when the Colorado Plateau was uplifted, oxygen started to arrive, and the microbes feasted on this iron carbonate and changed it into iron oxide.
That's not all we found here. There were these odd plates of oxide that didn't fit the Moki marble story. So one of the cool things about, one of the interesting geochemical things out here is there's different kinds of iron oxide cement and precipitated material. And there's a lot of the Moki marbles that you've seen, the spherical things like this, which have a rind in this area, which is mostly goethite, right? And then there's also fracture filling, what looks like it's fracture filling material. It's less obviously spherical, and in some places this fracture filling material actually has a very different texture. It looks like it's vitreous, looks sort of glassy, very shiny. It's still iron oxide, but it has an extremely different texture. And the samples of this vitreous, shiny iron oxide that we've dated so far have had relatively high uranium and relatively reproducible ages of 300,000 years, very reproducible, compared to the ages of these goethite rinds, which range anywhere from about 5 to 6 million years down to as low as maybe about 300,000 years. So this stuff may be the latest phase of iron oxide precipitation in this area. Not only are these the latest phase of oxide precipitation, but they're also pretty weird. On one side there are these giant rusty pipes in the rock that gradually diffuse into rust-stained sandstone towards the east. To the west it all ends, or begins, abruptly with a sheer wall. The way these things formed isn't clear, but it's got something to do with fluids and joints. So here we are at the edge of one of these half domes, as Dave Loop calls them, where we have a fracture which has on one side of it a lot of iron oxide precipitated in the form of tubes and flow structures that appear to be going to the southeast towards the Colorado River. But then right along the fracture is a precipitation of a kind of different kind. It's much more vitreous, dense, and pure iron oxide. It appears to have formed right in the fracture, not as cement filling the space around the sand grains downstream in the paleo flow direction. So this is what we're hypothesizing is the latest phase of mineralization, secondary mineralization of the oxide in this region. But that's not all.
On one side of that fracture, you see a lot of iron oxide striping. Commonly these are in the form of thick wall pipes, and the pipes are all oriented towards the southeast and
towards the Colorado River.
Yeah, and so we think that this may have taken place by the water moving through in this direction toward the southeast, and when it encountered these fractures, there was degassing of carbon dioxide, and that brought about precipitation of iron carbonate minerals, maybe mostly little BB-sized concretions. So that's phase one. You develop the iron carbonate cements on the downflow side of the fracture, and then the flow keeps going the same way, but oxidizing water starts to arrive, and that's when you generate these pipe-like concretions. Iron oxidizing microbes are involved there. But it's a different, for some reason it's a little different, that you don't create a little rind on each individual marble. It's more of a process that it's a batch processing.
And in the back, I wanna, and top it off, I want.